Cool. Yeah, thank you for letting me a chance to practice teaching. So yeah, last time we talked a little bit about distribution shift, and we also talked about these policy functions, where a policy is a function mapping a prediction to a particular action. And we said that, okay, if we have a predictor F that is calibrated or approximately calibrated, that we can actually use this function to estimate the loss of a particular policy without actually needing access to real labels from the distribution. Okay, so today we're going to go a little bit further and say, okay, not only can we get a good estimate of the loss of a particular policy, we can actually find the optimal policy for a given predictor. Okay? So first I'll start by recalling all of these things that I just said that maybe have fallen out of your brain in the last week. So what is a policy? Again, a policy, we're going to say we'll first fix an action space. Call that A, and also a model or predictor F, which will map from some data domain X. We'll say that it's making predictions its output is in the 0-1 interval. And a policy rho is going to be just any function that maps outputs of F to our action space. Okay. So we'll say it chooses an action. And again, this will be as a function of our predictor F. Okay, so it's not looking directly at X, it's just looking at the output of our predictor on X. And we also talked about estimating the loss of a particular policy, and we'll describe the expected loss of a policy for a particular loss function L. So let's throw that down here as well. So the expected loss of rho defined as follows. Again, we're going to have an action space as before, but now we have this loss function. Okay. And the loss function is going to take two inputs. It's going to take in an action. And in this case, we're only going to consider binary labels for pretty much all of today. So I'm just going to hard code that into the definition here. So the loss function will look at the action that we took, and then it'll look at a label, and it will penalize us accordingly, according to whatever L says we should do. So given, and this will, I should say, it'll output a real value. So we're not currently constraining the output of L to be bounded. We will in a moment, but for now, let's just consider all real valued losses. So given a particular distribution D, and we'll say this is over labeled examples from our data domain, and predictor F is again mapping examples into the 0-1 interval. The expected loss of our policy rho will be written L rho F D, and it's the expectation over D of the pointwise loss. And so we're drawing some sort of labeled example from our distribution, and then we're evaluating our loss function on the output of our policy Again, our policy is we're first applying our predictor to the example from our distribution. Make sure of all of my brackets. Okay, so right, we sample a labeled example from the distribution. We give the X value to our predictor. It outputs some real value. Our policy maps from real values to action spaces. And then our loss function maps from labels and action spaces to some real value. And so our expected loss is just the expectation of our distribution. Cool. And then what we talked about last time was this F estimated loss, right? So notably this loss here, to actually compute it, we need to see labeled examples from the distribution. But what we talked about last time is that we can actually get a pretty good approximation for this quantity by just using the probabilities that we get from F, treating those like real probabilities, and then using that to estimate the expectation. So, and we called this the F estimated loss. And we have an action space. Now we're thinking of a particular loss function, a particular policy, a particular predictor, and a future distribution. So again, we're not going to have access to labels, so we're just going to consider the marginal distribution over the data domain X. And the F estimated loss is going to be sort of what you might expect from what the estimated loss is. It's just we don't have the true probabilities, so we have to use the output of F to get our best guess for what the probability of seeing a 1 or a 0 is here. So it's the expectation of the output of F, which we're treating like it's a real probability. The loss of our policy given the output of F. And the label being 1, because again, F of X is sort of telling us roughly the probability that the label Y is equal to 1. And now we have to account for, well, what if the label is 0, right? So we have some probability, again, we're treating F of X like it's giving us real probabilities. So some probability that our label was 0, and then we're going to suffer some loss in this case as well. Okay, so again, we have no Y's anywhere in here. We're just sort of saying, okay, we have maybe an F of X probability approximately if F is calibrated of seeing a 1 and a 1 minus F of X probability of seeing a 0, and we can use that to estimate our loss. And we showed last time that this, as long as F is approximately calibrated, not too far away from this. So we proved the following theorem that we'll be using a lot today. And that's if we let C be the max over all possible actions. The loss of taking that action if we see a 0 plus the loss of that action if the label is in fact a 1. So take C to be this quantity if F is alpha L1 calibrated with respect to the distribution that we don't care about estimating loss on. Where the difference between the true loss and the F estimated loss will be bounded. By this term here, multiplied by our calibration error alpha. Okay, so this was what we did last time. Any questions about this so far? Okay. So now we're going to use the theorem that we proved last time to again show how we can find this optimal policy. So we'll start by considering a particular loss function. We'll be able to say this, say a sort of analogous statement for arbitrary loss functions, but just as a warm-up, we're going to consider a particular loss and then show for a calibrated predictor F what the optimal policy is to minimize that particular loss function. And using only the F estimated loss. Cool. So we're going to talk about binary classification. For those who aren't familiar here, the setup is pretty simple. So we're going to have a label space that is, as you might guess, binary. So we have 0, 1 labels. And our action space, in this case, is also going to be binary. Yeah. Our loss function we'll define as a 0, 1 loss. It's just going to be the 1 whenever we have whenever A and Y agree, and it'll be, or whenever they disagree, and it'll be 0 otherwise. So it's the indicator for A not equal to Y. So like one example might be, let's say I have like my data domain X here is pictures of cats or like actual cats, right? And I'm going to have some sort of label indicating how amenable this cat is to being pet, right? So maybe it's going to claw you if you try to pet it. So we're going to have action space, which is like pet the cat, don't pet the cat, and labels, which are like, is the cat going to claw you? Did the cat claw you after being pet? And you're going to be sad if you didn't pet a cat that you could have actually pet, like wasn't going to claw you. But then, if you do pet the cat and it wasn't safe to pet the cat, you'll be sad because you got clawed. So this is a case where you might want to use this sort of 0, 1 loss type of function. Cool. And we will show that if this is our setup and this is a particular loss function we're interested in, then the optimal policy to follow for a calibrated predictor is the following. Take your prediction. If it's greater than a half, output 1. So go ahead, pet that cat. You're probably safe. And if it's less than a half, then like maybe don't. Maybe it's like don't pet that cat. It'll probably scratch you, and so you don't. Okay. Questions about the policy, how it's defined? Yeah. We want to bias towards petting the cats. Live dangerously. Okay, so we're now going to prove the following theorem for this specific 0, 1 case. So and we're going to fix the distribution D. Fix your predictor F, which again, outputs. And we'll say that the L1 calibration loss of F with respect to D, or the calibration error, I should say, is alpha. So we're alpha approximately calibrated on D. Then for any other policy, that we might have considered. That's not sort of, extremizing the probabilities. It will follow that the loss of our proposed policy is not much worse than the policy that you chose. So, and again, sort of emphasize this is the actual expected loss. We're not talking about estimated losses yet. We will, however, potentially be a little bit worse, and will be worse in proportion to the calibration error of F. Cool. So let's go ahead and prove this. We'll start by doing the fun work of just expanding out what the loss is. Take that back. First, we're going to actually use our lemma from last time, and we'll say, okay, we know that the true loss isn't too far away from the F estimated loss. So we'll start there. And lower bound the true loss by this F estimated loss. And now I'm going to break out, I'm going to both sort of expand out the F estimated loss definition and simultaneously break out the expectation into two sums. I'm going to sum over every place, every V for which our policy outputs 0, where it says don't pet the cat, and then every value V for which the this policy row says, okay, or everywhere where it says 0, everywhere it says 1. So it'll be the sum over all V in the range of F, where our predictor, or rather our policy, outputs 0. The probability. And maybe I'll drop subscripts for a bit, unless people find it confusing to not see them, and I can bring them back. So we want to sum over LV the probability that our predictor actually output V, and then the F estimated loss for that particular V, which will be again V times what is in here? So again, here we're looking just to the case where our policy is 0. And so the losses, I guess the first argument to the loss, point-wise loss here will always be 0. And then we need to sum over the rest of the V's. And so again, what is our estimated or F estimated loss here? Well, same as before, only now our action is 1 instead of 0. Cool. Okay. So we know the particular loss that we're dealing with here, right? We're dealing with the 0, 1 loss. And so notably, when our action and the label agree, this is just going to be 0. Similarly, this is going to be 0. And these are the contributions that we're going to be left with. Yep. And again, what we want at the end of the day is, right, we want to be able to compare to the optimal policy, where if V was greater than 1/2, we output 1, and then if V was less than 1/2, we output 0. So let's sort of like stare at this for a second and think about the contributions to this total sum from the case where we took action 1, but the label was 0, or where we took action 0 and the label was 1. So if we took action 0 and the label was 1, we suffer V loss, right? We get a V contribution to our total loss. So if V is greater than 1/2, right, we actually probably would suffer like less loss, right, if we had actually output a 1, right? So if we're suffering 1 minus V everywhere we take an action, or everywhere our action is 1 and we're wrong, then this quantity here is, right, going to be less than 1/2 anywhere V is greater than 1/2. Likewise, this will be less than 1/2 anywhere V is less than 1/2. So if there's any sum V, or any particular V, where we're or we're choosing action 1, but V is less than 1/2, we'd actually do better if we chose action 0, because then we only suffer a loss. We only get a contribution of V to the loss. Right. So let's imagine we take every V where this is true, every V that's less than 1/2 here, for which we're taking action 1, and we sort of like shift it over here. We instead take action 0. Right. And similarly, if V was actually less than 1/2, but we were taking action 0, we know that shifting it here can only decrease the contribution to the overall loss. So we'll just sort of swap the appropriate points. And oh, hey, now look, we've like ended up with exactly rho star as our policy. Okay. So in particular, we can say that this whole sum here can't be any less than the analogous sum if we swap out rho for rho star. So if instead we say, we just break these two sums into cases where V is less than 1/2. We get this contribution to the loss, and if we sum over the rest, and so this is after we've done our little swap and sort of acknowledge that again, like these terms aren't contributing anything. We'll get this expression, and then this is exactly the F estimated loss of our optimal policy rho. And I guess notably I've been dropping alphas here. So it should be a minus alpha as well here. Cool. But again, at the end of the day, we wanted to say something about real loss, not alpha estimated loss or F estimated loss. And so again, we'll apply the lemma that we proved last time, say that, okay, the F estimated loss is only going to be alpha away from the actual loss. And so we'll get another factor of alpha here. Cool. We're able to show for the special case of 0-1 loss that we can, without access to the labels at all, figure out the optimal policy rho star for a given calibrated predictor F. And then we know that the loss of our optimal policy will be not too much worse, about like 2 alpha worse in the worst case, compared to any other policy we could have chosen for F. Questions about this? Okay, so I promised you earlier that we would consider more general loss functions, and not just the 0-1 loss, which is very, very special and only really applicable to cases where you're trying to decide whether or not to pet potentially ferocious animals. So let's consider what we might do for more general loss functions. Okay, so I claim that this row star here is sort of, again, a special case for the 0-1 loss of the following policy. So for a particular loss function L, I'm going to literally just pick the action that minimizes the loss. This is right. So I will look over my action space. And I don't actually need labels to be able to compute the F estimated loss. And so all I really need here is V, and I need to know what my loss function is, but I have both of those. So I can actually just pick the action that minimizes this quantity. And I'll be good to go for any particular loss. Okay, now how is that going to change this proof here? And the answer is like not really significantly, right? So a few things have changed. One, we only ate an additive factor alpha here from the calibration error because our 0-1 loss is bounded, right? It's bounded in 0-1. And so this C quantity here is going to be 1. So if we don't know that anymore, we have to sort of plug in this generic C everywhere. That's not too bad. Normally we want our loss functions to be bounded by something anyway. And then again, like nothing actually written, nothing particularly changes here other than the fact that I won't be breaking things up like particularly this way anymore. I'm just saying, okay, I have some policy here, and I know that if I am point-wise minimizing this expression, then I can by swapping out row here for row star, I can only decrease this loss because I'm decreasing point-wise terms, and therefore my loss can't be too much worse. So really only what's changed quantitatively is this additional factor of C. Okay, so this is pretty neat, right? So now we know that if we have a calibrated predictor, we can find an optimal policy to take based on that predictor. We can compute this optimal policy just using the calibrated predictor itself, and treating the probabilities that it gives us as though they were the actual probabilities when estimating losses. And again, we know that the loss of our policy, right, won't be too much worse than any other policy we could have taken given F. Okay, so now the question is, does this help me say anything about the loss of a particular policy compared to any other function, right? Maybe this function doesn't just depend on F of X, maybe this function actually gets to look at X itself, right? Can I say anything now about the loss of my policy, my optimal policy compared to that function? The answer is no, not yet. Okay, so for the rest of this class, we're going to talk about how strengthening our calibration condition to multi-calibration will allow us to sort of say the stronger thing, right? So what we'd really like to do in sort of the loss minimization setting is fix in advance some class of functions we want to beat, okay? And we want it to be the case that we can find a predictor, F, and then if you come to me after I've trained F with knowledge of this class of functions I want to beat, if you come to me and say, hey, minimize this loss, that I can now post-process the output of my predictor, right, using some sort of policy, and then be guaranteed that the loss of that policy won't be too much worse than anything else in this class, H, right? So here we've done something like that, but only considering, we're only comparing the loss of our policy to other policies of F, right? But there's like a whole wide world of functions out there, and that's really what we want to compare to. And in order to do that, we're going to need to strengthen our calibration condition to multi-calibration. When, as I guess like a spoiler, we're going to want to be multi-calibrated with respect to the class of functions that we want to beat. So questions about why we want this, why this is cool. It's pretty cool, right? So it essentially means that I can like train a predictor without knowing my loss function, right? You can tell me the loss function afterwards, and then I can post-process predictions without having to go back and retrain a whole model again and do all of that, like, you know, really costly computation, and still get something that'll like approximately minimize that loss function that you just gave me, again, compared to anything in my reference class. But first, we're going to have to like set up a whole lot of machinery. So we'll introduce some definitions and make some claims. It'll be a good time. Yes.
How many interesting loss functions are there restricted into binary?
How many interesting loss functions are there?
Yeah, like I can make
So I guess like there are a whole bunches. I guess like there's exponential loss. There's like quadratic loss. There's hinge loss. That's a loss that I hear people like sometimes. You talked about pinball loss, I believe previously. Is that does that need real valued labels? Okay. Yeah, fair. But yeah, there are bunches of losses. Like a lot of times what you actually care about optimizing, right, it might be just this like binary classification sort of setting where we have a 0-1 loss, but like this is maybe hard to optimize directly, and so you'll have some sort of like surrogate loss instead, something that's maybe like nice and convex and lets you do gradient descent to actually find a good function. Cool. Okay, so going forward, we're going to be interested primarily in convex loss functions. Just a reminder of like what it means for a convex, for a function to be convex, and in particular, a loss function to be convex. So we have our loss function. We're going to consider action space to be, rather than the sort of binary action space we're considering before, where we're either taking action 0 or action 1, we can now take any action in the 0-1 interval. Again, our label space will be binary. And we'll say that this loss function is convex in its first argument. So notably the action argument rather than the label. If it's the case that for all labels, we might have all two of them, that, once we sort of fix the label, the resulting function is convex. So say the loss of alpha v plus 1 minus alpha is like some v prime, I should say. So essentially what we want to do is we want to pick two points like v and v primes, but consider the line between them, or like any point on the line between them. And it should be the case that if we evaluate the loss, the point in the line between them, that this is less than or equal to alpha times, it's like the point on the line between the functions, or between the losses. So alpha times the loss of action v label y plus 1 minus alpha times the loss of action v prime and label y. Okay, so this is just like the standard convexity definition. And why do we care about this? Well, we care about convex functions because they let us apply Jensens inequality. So let's remind ourselves of what Jensens inequality is, or maybe there's a lucky person who's seeing it for the first time. That'd be great. So Jensens inequality is going to let us relate the expectation of a function with the function of the expectation. So in particular, we care about loss functions. So I'm going to say fix any loss function L. Again, it has to be convex in its first argument here. Then for all label 0, 1, and any distribution P, and we'll say it's from the space of like distributions over this 0, 1 interval. We have that the expectation of V, sampling V from P of the loss of V in label Y is greater than or equal to the loss of the expectation of V. So again, we have this universal quantification over Y, so we're sort of treating that as fixed here. And again, we're taking expectations over this distribution P, which is also universally quantified. Cool. We'll need another definition. We're going to like further qualify the space of loss functions that we're going to be able to say something about here, or restrict it to L. Lipschitz loss functions. So what is an L. Lipschitz loss function? So it's L. Lipschitz, I should say, again, in its first argument. So the thing we care about here. If for all B prime, for all 0, 1 labels, the difference between the loss at V and Y and the loss at V prime and Y is going to be smaller than L times the difference between v and v prime. Yeah, so we're just saying that like our loss function is not growing too fast as a, over small regions. Cool. And in a second, we're going to prove something about alpha multi-calibrated predictors. And so I just want to like throw up that definition again so we can all remember what it is. Question is, can I fit it in this space? We're going to try. Okay, so L1 multi-calibration for real valued functions. So we're going to fix a distribution D. And this is over labeled examples by pairs. Fix a model F. And we'll also want to define a class of functions. So let H be a collection of real valued functions. On X. We'll say that F is alpha approximately L1 multi-calibrated with respect to D. And this class of functions H, if for every function in this class, the following holds. So we use this K1 notation. Only right to indicate multi-calibration, we have this additional function parameter here. And it should be the case that for every H, when we sum over V and the range of F, the following holds. We take the expectation, again, this is over D, of the function H from our larger class on X, and the difference between X's label and this value V that F predicted. This is all here. Again, conditioning on having F having predicted V here, that this is all less than or equal to alpha. So if you think of, I mean, we want to consider real valued functions here, but let's say that H were binary, was sort of representing maybe a particular set of inputs that we want to be calibrated with respect to, then we'd just be asking that, okay, if X is in H, then we still need to be calibrated if we just look at our distribution restricted to H. But again, we want to sort of generalize this to consider real valued functions H. Cool. And I should say, like, the straight away multi-calibration does not necessarily imply like regular vanilla calibration. Okay, that in order to get that implication, I have to make a certain assumption about H. Notably, I have to assume that H contains the constant function 1. Okay, so again, if H is just 1 everywhere, then I'm going to force, if I'm multi-calibrated with respect to my class of functions, now then it has to be the case that I can just set this H of X to 1, and then I recover the original definition of calibration that we all know and love. And so for all of the theorems that we prove for the rest of the day, we're just going to go ahead and assume that H contains this constant function that is just 1 everywhere. It's 1 for X. Okay. And this is just to save us from having to write out like that F is both multi-calibrated and regular calibrated. So now that we have all of our machinery, we can start trying to prove cool theorems. Okay. So first, we're going to prove a useful lemma about multi-calibration, which says that if we have a predictor F that is multi-calibrated with respect to some class of functions H, and we pick out, it should be the case, I guess, that for all H and H, if we condition on the label being Y, or label being like 1 or 0, that the expectation of this function doesn't change too much. Okay, I guess I conditioned on a particular prediction value V for F. So let me write out what that statement actually is real quick. So again, we're going to fix our distribution D and the class of functions H that will be multi-calibrated with respect to. And we'll say that F is approximately L1 multi-calibrated with respect to D and H. Then for any H and H you like, and say we have the following. Yeah.
F in H? F comma H?
Oh, sorry. I was using this as an abbreviation. Sorry, this is just like function class. So yeah. Sorry. So we have this function class H. Yes, thanks. Cool. Then yeah, for any H and H, it should be the case. If I look at the expectation of H, conditioning on f of X being V, and the label being 1. And the expectation of H conditioned again on f of X being V, but now the label being 0, that this is also bounded. In particular, it's bounded by 2 times the multi-calibration error. Cool. So this is like a kind of an interesting indistinguishability criteria. So if we consider like, we're going to restrict to a region where f of x is constant, look at this region, then these functions that we're multi-calibrated with respect to aren't particularly good at in aggregate distinguishing ones and zero labels, right? So we're sort of in some sense saying that if we're multi-calibrated, that H is not, H is not going to be like particularly informative within these like level sets of F. Okay, so let's prove this lemma.
Sorry, what is the reason? I'm trying to get the intuition for having that with multiplicative potential on this.
Yeah, so this is a great question. And Erin, feel free to add something if you have something more clever to say here. This is just like sufficient to prove the Kohler theorem we're going to prove in a minute. So you could have like a stronger condition where that's not there, but we don't need that. So yeah, do you have anything maybe more inspiring to say about the sort of scaling factor of v and 1 minus v?
No, I'll just ask you the question. Is the lemma still true if you get rid of that v times 1 minus v?
I thought about it for a little bit, and I don't. There might be like an alternative approach, I think, and it seems like maybe it ought to.
I was surprised when that popped out.
Yeah.
Yeah,
So I remember I was also you are right, I think, to be spiritually troubled by this. So I will leave that as an exercise to the class.
Yeah, I actually would be interested in how to prove this without the v.
Yeah, please email us if you figure that out.
This doesn't show up in the paper this lecture draws from, but they're using slightly different definitions. So when I tried,
Yeah, they're
up
using
these
like the
definitions,
actual covariant,
they're
yeah,
using covariance.
the
So
covariance
when I tried with
definition,
these
yeah.
definitions, I think that's more like the v times 1 minus v comes out, but I don't know. That's there.
Yeah.
It doesn't actually hurt the final theorem. So
Yeah, exactly. You can still prove the same thing. But yeah, it would be fun to do. Okay, so we'll start from multi-calibration. So we know that the calibration error is less than alpha. And then we'll just expand this out. The definition that we just wrote up or just erased. So we know that the sum of, again, the probability that f of x equals b times this expectation of h of x times the difference between the label and our prediction. So that this is just what we have from the definition of multi-calibration. And we'll further expand this out, right? So ultimately we want to start, we want to eventually get to a statement that's conditioning on the actual values of the labels. So let's rewrite this with, sort of with that in mind. We'll sort of start conditioning or looking at actual label values now. So this expectation is going to be expectation from the previous line is going to be the probability that the label is 1, conditioned on f of x being v. multiplied by this expectation. Expectation of h of x conditioned again on f of x being v and the label being 1. And now again, we're conditioning on the label, and so we can pull out this term. And so we get a 1 minus v here. And this will be a plus the probability that y equals 0 conditioned on f of x equaling v. Again, multiplied by the expectation of h of x, conditioning on the same. The label is 0. Only now, once we're conditioning on y being 0, this is actually negative v. So we'll switch this plus to a minus. What I do there? Cool. Okay, so if it were the case that our predictor was like perfectly calibrated, right? None of this like approximate calibration. What would this quantity here be? Yes. Yes, exactly, right? So if we're perfectly calibrated, then we're outputting v exactly when the true probability of seeing a 1 is v. And so let's sort of separate the sum out into two terms, the term where we pretend that f is perfect, and then some error terms from the fact that f isn't actually perfect. Similarly, we can pretend that this is 1 minus v. So we've replaced this probability with just the value v, and we have v times just the same thing, expectation of h of x, conditioning on f of x equaling v, and y equaling 0. And this was, or sorry, y equaling 1, jokes. It's being 1 minus v. Then again, we're replacing this with 1 minus v. That's the same old expectation of h of x, conditioned on the label being 0 and f of x being v. Okay, so this is the easy part of this term, right? This was just sort of the ideal world where we imagined f of x was really perfectly calibrated, but it's not. So these estimates here for the probabilities will be off. In particular, so if we define case of v's to be like the contribution to calibration error from any particular v, then our error term will be bounded by the contribution from, or the sum over all v's, the calibration error contribution from the particular v times 1 minus v plus v, right? Because so we're subtracting this again because what we're looking for, we're trying to upper bound everything by alpha. So the worst case for us, right, is that this will be we'll end up having to subtract this, and we know that these expectations can't be greater than 1, right? We're looking at value expectations of values that are between 0 and 1. And so in particular, they can't be greater than 1. So we're not hitting our estimation error of these probabilities with anything too big. And then we also have to consider the fact that, we're multiplying by v here and 1 minus v here. And so we're going to have all of these factors in our slop term over here. But I screwed up the parentheses. So what we have is the error term being the sum over all v of the contribution to calibration error for a particular v, multiplied by 1 minus v plus v, otherwise known as 1. And so this is just like the sum of all of the contributions to the calibration error. So this is bounded by alpha here. Cool. Okay. So we've done a decent job bounding our error term here. And now we see that we have common multiplicative factors here, right? We have a v and a 1 minus v, and similarly, we have a 1 minus v and a v. So let's factor those out front. This is where your beloved terms are coming from, by the way. What's left is just the expectation of h of x. And again, we're conditioning on our prediction. And the label being 1. Yeah.
I think I missed how you got these to the third line. What are you adding?
From the second to the third line here, I'm replacing this probability with v, because v is given that our predictor f here is calibrated or approximately calibrated, right? It's like if we had no alpha term whatsoever, if we were 0 or calibrated, then this just would be v,
Okay,
right?
And, the sum
And then
term is
it's
making up for the-
yeah, the sum over here is the slop. So like these k sub v's are the contributions to alpha from each individual v, because for each v, right, we're sort of looking at the sum, or I guess the calibration error alpha comes from the sum over all v in the range of f, and looking at how much once we condition on our prediction being v, how much the expectation of the label differs from v, right? So there's sort of like this kv contribution. And we can't like necessarily cleanly factor this out because we don't necessarily know what's going on with these expectations, but we do know that the expectations are less than 1. And then we also have to consider the fact that we have these multiplicative terms, right? So we could eat, like in the worst case, we could eat a 1 minus v times kv from this term, and we could eat a v times kv from this term, but then adding these together, and that's just.
So when there should be an inequality, right?
Yes, thank you.
And is it going in the right direction?
Right, so we're subtracting off the error, and so that'll be smaller, right? So yes. Yeah.
You might write down the definition of KP.
Oh yeah, absolutely. I'd be happy to do this. How about over here in this little corner? So again, like the calibration condition was saying that, if we summed over all V's, that the thing I'm about to write, the sum of all of them, will be bounded. And the KV is just naming each contribution to that sum. So we said the probability, or we're predicting probability V, but then like the true label expectation was something else. And so that's the difference. Yes.
So each step here seems pretty tight. You said maybe there was some other derivation that would get rid of this V becomes 1 plus V, but like, where is the slop in this inequality? It seems like,
Oh, sorry. I guess the thing that I think where there might be, no, never mind. I take it back. No, yeah, I'm not. Let me think.
like the V times 1 minus V appears to come out of this calculation in a pretty natural way.
Yeah. So I think if so I guess the definition that we're using here for multi-calibration for real valued predictors is also a little bit different from the covariance definition that's used in that paper, notably. Sorry, so if do I still have the calibration definition somewhere? So sort of like a fun aside. So our definition of calibration says something about the expectation of h of x times y minus v conditions on f of x equal to v. And then this is not quite covariance unless v is the actual label like this is not a, right? So yeah, I guess like if, yeah, whereas I think the definition there they use sort of implies this other, I think it's maybe like implying, because I guess if you wanted, if you have this covariance thing where we're now saying h of x is bar times y minus y bar, condition on, this is all less than alpha or something, then, right, this is equal to the expectation. I've like, yeah, I don't know, I've been finding this like mildly troubling for a little while, but this is equal to this, right? Because you get a -2, but then this is positive, and so, right, and you get the same term up here, right? If you sort of multiply this out, okay, we'll get our expectation of h of x times y. But now we have this. And so if v is in fact the label expectation, then they're the same. But so I think that's the only place it could be coming from, right?
But like, right. But like if ours is calibrated, I don't know.
Do we really care about the 2?
Yeah.
Alpha, like upper bounded by 2. So if we make it 8, just trivially fill off with 1 minus b, right? So that's going to make the entire sum go smaller. Looking at this, since d is like somewhere between 0 and 1.
Right.
At most, it's 1/4. Pull that out of the sum. Multiply both sides by 4. You can upper bound by 8.
I think that goes in the wrong direction. The problem is the V times 1 minus V might be very small.
Yeah, so like if you get rid of this, yeah, or exactly what they said, like maybe you zeroed out a term here, like because v was actually 0, or if v was 1, you zeroed out a term that in fact had a large deviation. But more ideas, yeah. Please keep them coming. Okay, sorry, so those were the KVs. And to sort of finish what we were saying here, right? This is like the last step. We're just saying that the difference between the expectation of h of x conditioning on v and label 1 it's not too different from the expectation when we condition on the label being 0. Okay. I think this is probably a good place for a break. So we can take like, I don't know, we want to start again at 3:10, and we can prove a super cool theorem showing that multi-calibration with respect to class of functions H allows us to get a predictor that we can post-process to have loss like not much worse than any function from H. And that will be like our final proof. Cool. If other people have questions or ideas about how to resolve this, would be awesome. All right, cool. So yeah, so now that we're back, we're going to prove this awesome theorem that says a multi-calibrated predictor will give us something that we can post-process to minimize any loss. When I say any loss, I mean highly qualified loss, because we saw these things about convexity and Lipschitzness. But we'll be able to post-process our multi-calibrated predictor to do about as well with respect to a particular loss as anything else in our class of functions that we were multi-calibrated with respect to. Let's get rid of the proof. I'll maybe write up like a brief proof sketch so we can see how this is going to go. Or maybe I'll write down what we're actually trying to prove first. Let's do that. Okay. Cool. So we'll have a bounded loss function. And it will be, let's say it's both convex. Be able to use Jensens Inequality and Lipschitz. So we know it doesn't grow too fast, small perturbations to its input. And again, we only really care about these properties with respect to the first input, with respect to the actions that we're evaluating our loss on. Okay. And suppose I have a predictor F that is alpha approximately L1 multi-calibrated with respect to distribution D and some class of functions H, particularly real valued functions. Okay. Furthermore, we're going to pick the following policy to be sort of like our optimal post-processing for a particular loss function L. So let rho star sub L be the policy that minimizes our F estimated loss. It's, so again, what this policy is doing, it says, okay, like tell me the loss function that I'm supposed to be post-processing for, and give me as input an estimate for, a probability of seeing a 1 as my label. Then I'm just going to give you the action that minimizes the expected loss, where I'm using this estimate for the probability to actually compute the expectation or approximate the expectation. Okay, so let's fix this policy rho star. Then the loss of rho star is going to be not much worse than the loss of any other function from this class H. And so notably, it can't be that much worse than like the best possible function from our class. So here I'm just writing out the actual expected loss. And then we'll have this slack term here. So, we won't do too much worse, but we could do a little bit worse, where a little bit we4 plus 4L, or L's our Lipschitz factor for the loss function we're trying to minimize, all multiplied by our calibration error alpha here. Cool. So now that we know what we're trying to prove, let's talk about the proof idea. So the first step is sort of the only thing we haven't really done yet. So we want to, we're going to try to bound the loss of any other function H from our class H. And we're going to show that it has to be greater than the F estimated loss of some policy rho, not necessarily this optimal policy rho, but we're going to cleverly come up with a policy rho such that we can lower bound the loss of a function from H by the loss of this policy. Cool. So that will be step 1, and that will be the part that requires some cleverness. H. Greater than the F estimated loss policy rho. Cool. Step 2. Well, we know just sort of like by definition of what the optimal policy rho star here is doing, right? It's minimizing the F estimated loss. So the F estimated loss of the thing minimizing the F estimated loss ought to be lower than, right, whatever the F estimated loss of the alternative policy rho here is. So we can further lower bound that by the F estimated loss of rho star. Cool. And step 3 is again using the fact that F is calibrated to say that this F estimated loss is actually pretty close to the real loss. And so in particular, we'll be able to say that, okay, the loss of this function H, like for any function from our class, has to be, like not too much better than the actual loss of our optimal policy. I'll use the, like there's going to be a slack term here, but the F estimated loss will be approximately the real loss suffered by this row star policy. Cool. So we already have this proof. And this is just going to follow from the definition of row star. And so the real work we have to do is figuring out how to sort of connect the loss of H to a policy, right? So a policy can only really look at the output of our predictor, F, whereas arbitrary functions from our hypothesis class can look directly at elements from the domain. Okay, so this will be the challenging part. So do folks want me to write up what the KVs are again? These are the things I was saying are the contributions to the calibration error from each individual V. I'm going to do it. Okay. Just for fun. So again, the case of V's are the error in calibration for a particular V. Cool. Okay, so starting off, again, starting from what we know from alpha multicalibration, we know that our, sorry, we'll start there. Let's just start with the actual loss. Okay, so the actual loss of this function H we can break into a sum over, again, all of the V in the range of F, as well as a sum over the two choices of label Y. Okay, so our loss can be expressed by the following. Versus. So it's the probability that we predicted V times the probability of having of seeing label Y, given that we predicted V, times the expected loss of H of X, given that the label's 1. Since we're conditioning on that. And then we'll do the same thing again, but this time conditioning on label being 0. Only now, we're looking at the loss when the label is 0. Cool. So do people buy that this is a way we can express our loss, right? We're just sort of looking at all of the level sets of our predictor and then saying, okay, let's look at individually the case when we saw label 1 and the case where we saw a label 0. So now we're going to use Jensens inequality because our loss function is convex in its first argument, we can move this expectation inside the loss function, right? So we can say that this quantity here will be greater than the same sum, except now we're looking at the loss of the expectation of h of x. And let me fix some notation real quick to save us having to write a bunch of nasty expectations. So I'm just going to fix some shorthand real quick. For the expectation of h conditioned on f of x being v and the label being 1. So we'll say that's HV1 here. Similarly, we'll define HV0 to be the expectation of h of x oops. When the actual label is 0. Okay, so this is, we're not doing anything profound, but we are fixing some notation. So again, back to using Jensens inequality here. Have that this is greater than or equal to the probability f of x equals b. And I guess save yourself some writing. We'll at the same time do the same trick we did earlier, where we swapped out v here and similarly swapped out 1 minus v here, and then had to absorb an error term outside of the sum. So we'll do that while we apply Jensen. So we'll have this v times the loss of HV1. And the label is 1 plus 1 minus v. Again, that's coming from here, times the loss of HV0. The label is 0. But each time we did the substitution, we had to, each time we substituted in the actual value v or 1 minus v for the conditional label probabilities, we absorbed potentially the calibration error slack factors over here, and so we have to dive them back over here. Okay. And I guess we can further say so this is just 2 alpha. So we're looking at the sum overall such KB. All right, so let's back up a second. Because we're still in step 1 here. We need to figure out some sort of policy to relate this loss to, right? That was the goal for this step. And what we have here, again, we wanted to say, okay, the loss of H is greater than the F estimated loss of a policy row. And what we have here is starting to look kind of like an F estimated loss, right? If you remember, the F estimated loss was going to be V times the loss of our policy when the label is 1, and 1 minus V times the loss of our policy when the label is 0. But this is really, if we, or again, we're just pattern matching, what looks wrong here. The fact that this is not Like these things are not the same. This is not a policy, right? A policy just looks at V. Here we have H, which is looking at the probability V, but then also the label. And so we can't really call this a policy yet. But we shouldn't be too upset by this because we just proved a cool lemma showing that once we've conditioned conditioned on V, that these quantities are actually kind of close, right? We said specifically, if we are multi-calibrated with respect to H, then it has to be the case that the expectation of H when we're conditioning on the label doesn't change too much, okay? So why is that good for us here? Well, it means that like, okay, potentially we could just ignore the label, right? Like maybe we can just pick like a particular one of these to go with everywhere. And then that's a policy, right? Right. Like everywhere I would have used H of V with label 0. I actually just swap in H of V with label 1 and know that that's not too much different. Okay, that's like one thing that we could do. And that sort of turns this H into an actual policy, and that turns this expression into an actual F estimated loss. But okay, some stuff is still not quite right about this so far. So we know that these two things are close, but that doesn't tell us anything about the loss, right? Like we actually don't know that that doesn't perturb our loss too much, except for the fact that we specified the loss has to be Lipschitz as well. So then the fact that these quantities, like if we could come up with a policy such that these quantities are close, which we should get from the one that we just proved, then the Lipschitzness property of our loss will be enough to say like, okay, you didn't actually perturb the loss by too much either. Which means that we could, that we should have some hope, I guess, of picking a policy cleverly enough such that we can go from this expression to the F estimated loss for a particular policy. Okay. So the question now is, we're going to absorb some error, right? So like the slack term over here is going to grow when we, inevitably like swap out H of V1 or H of V2 for a real policy. So what is a policy that we can pick that will sort of minimize the slack term that we have to absorb, will minimize the error that we add on by comparing to an actual policy. So I claim something sort of like our cat petting policy will also work for this case, right? So I consider rho V, and if V is greater than 1/2, then my action is going to be whatever, going to actually output the expectation of H of X conditioned on F of V being V and the label being 1. Okay. And I'll put HV0 otherwise. Okay, so this is the policy I now want us to compare to, right? Or we're going to compare the loss of, we're going to like look at the loss of, or F estimated loss of this policy, and then compare it to the loss of H. And the reason we sort of, we're talking a second ago about saying, okay, maybe we can just pick a particular H and just go with that everywhere. But notice that like, okay, if we swap out here, if we swap HV1 out for HV0, that would successfully give us a policy where just HV0 everywhere. But if V is greater than 1/2, then I'm going to be eating a V, I'm going to be multiplying whatever error I get from swapping this out by something that's greater than 1/2. And so by being a little bit like more discerning here, by saying, okay, like I want to eat the smallest multiplicative factor in my approximation error that I can, by taking 1 minus v when v is large and v when v is small. I can do a little bit better than just having like a picking one of these two and going with it everywhere. So let's go ahead and use that intuition. You know, that we're sort of aiming for comparing to this policy at the end of the day to complete our proof. So in particular, if we swap out, if we swap this out for HV0, we can use Lipschitzness to bound how much that'll hurt us. So we've swapped out HV1 for HV0 here. And we were multiplying that loss by V. So we'll have this error term of V times L times the difference between the input and the one we swapped it out for, which is the difference between HV0 and HV1. Okay, and that's what we did whenever V was less than a half. Right. Swap this out for this, and then we still have to look at what happens in the other case when V is greater. And this time we absorb a 1 minus v multiplicative factor in addition to our Lipschitz factor. And that's for swapping out HV0 with HV1. Great. Okay. Cool. So ignoring these sort of Lipschitz terms over here, this now looks like a real F estimated loss, right? Like we here, this is, we're now looking at a policy, and that this, we're not looking at a label anymore, right? That we're just going to, you know, given V, if V is less than a half, we are taking action HV0. And if V is greater than a half, then we're always taking action HV1. So this is equal to the F estimated error of this policy we just defined, minus 2 alpha term, and again, minus this Lipschitz parameter. So probability f of x equals b. And sometimes we're multiplying it by v, sometimes we're multiplying it by 1 minus v, but we're multiplying it by v when v was less than a half, and 1 minus v when v was greater than a half. So we can just say the minimum, we're multiplying it by the minimum of v and 1 minus v. And again, our multi-calibration condition gave us a bound on this, because in the lemma we proved gave us a bound on this. And the min of v and 1 minus v is smaller than v times, or rather, sorry, is greater than v times 1 minus v. So that's actually what we need to truly like invoke our multi-calibration condition, right? Because as you pointed out, we have these weird v times 1 minus v terms showing up in the bound on the difference between expectations that we get from multi-calibration. But that's fine because those will still be here. So sweet. So we can now finally bound this by alpha. And this whole thing here. And yeah, so now we have I seem to be missing an extra factor of 2. Interesting. So I've now been able to bound the, oh, I know where it comes from. Aha, great. So we're still in like the world of f estimated loss here, right? So we have bound the loss of a function f by the f estimated loss of a particular policy plus these error terms where we'll have a minus 2 alpha minus L times alpha coming from Lipschitzness and calibration. So now we need to relate this to the loss. We need to go on to step 2 and relate this to the loss of our optimal policy. With what remaining room we have. So we're still looking at F estimated loss, but we're now comparing to rho star. And so we're going to have this factor of 2 alpha. So we'll additionally like eat from moving from rho to rho star. Oh, sorry. Yeah, this is just true. We don't eat anything from this. Sorry. Yeah, so this is just from the definition of the fact that rho is optimal. So as long as we're staying in the land of F estimated loss, we don't lose any factor by just saying, okay, if we compare to the minimum or the minimizing function or minimizing policy, good. But then we will eat another factor 2 alpha once we move to comparing to like the real loss of rho star.
Maybe I think that's the line where you go from the min of v to just v times the loss.
Yes.
Don't you have to pay for it? It doesn't have 2 that.
How does a 2 show up there? So I want to show that this is
start by multiplying by the extra term of the one
Mhm.
if you're making the thing, you're subtracting off somewhere. So normally.
Oh, because it's negative.
Normally you'd make this sign. This
So,
bigger.
so I'm actually,
But like, but this is the step where it was actually important that your policy makes a decision based on whether V is greater than 1/2 or V is less than 1/2, because since you're already multiplying by the minimum of V or 1 minus V, the extra term you need to add in is greater than 1/2. So you can make up for multiplying by this extra term that's greater than 1/2 by 2.
oh. Thank you. Thank you. Okay. So we should actually have a 2L alpha here. Okay, but then we will absorb yet another 2 alpha when we look at the true expected loss. But something still seems wrong because I have a 4 alpha there. I think in the notes that we have like a factor of 4 alpha. Or a factor of 4 in front of the L. Is that from the bound on, okay. It is in fact, yes, because the bound we actually got on this is not alpha, it's 2 alpha. So sorry, there's a factor from moving from min V 1 minus V to V and 1 minus V. But there's also a factor because the bound we have on this is 2 alpha, not alpha.
The claim is min of V 1 minus V is less than or V1. Right?
Or is less than 2.
Start 2.
Yeah. Yes. Cool. Cool. And now what is on the board is more or less consistent with notes, which is deeply reassuring. Cool. All right. So what did we just prove? We said that, okay, we are alpha approximately L1 multi-calibrated with respect to this distribution D and also a class of functions H. And then what we proved is that if I take arbitrary function H from this class, that the loss of this H has to be greater than the loss of our optimal policy over here as a post-processing of our multi-calibrated predictor F minus some slack term. So in particular, the loss of the optimal policy will be less than or equal to the loss of any function in H plus this 4 alpha plus 4L alpha term. Which again is like pretty cool, right? So like I can come up with like a multi-calibrated predictor with respect to a class of functions. And then if like my sentiments change about what I think a good model of loss should be, then I don't have to like retrain my model again. I can just use the same multi-calibrated model and just choose a different post-processing, right? There will be a new row star for a new loss function, but we'll be able to compute this post-processing efficiently, and we can still do as well as anything in our reference class. Any questions? Yes.
How does this generalize to multi-class?
How is this generalized to multi-class? Great question. Okay, so the notion of calibration will change as well, where instead of looking at I guess we have more than just like binary labels now, so we need to say something about all the different possible labels. So we need to sort of maybe we'll need a different notion of multi-calibration that will imply actually, I'm not entirely sure. I want to say that it'll need to imply closeness for these expectations conditioned on any of the possible labels.
Because it requires full distributional calibration, like in general, in like a multi-class setting, the thing that is output by F will be a vector that will predict the probability of every label. And something you could ask for, which would be very strong, is full distributional calibration. So
Okay.
You're correct, conditional on the whole vector of probabilities. But it would be nicer not to ask for that, because there's exponentially the number of labels, many set vectors.
Yeah, so the way that I think the Omni predictors paper deals with this is it just maps rather than having a vector of outputs, you just map to the 0-1 interval where you assign some chunk of the 0-1 interval to each class, and then you use this instead. But then you're not really using it as you're not using the output of F as a oh, right, because that right. Sorry, I forgot that they do like the weird partition thing. So I'm not sure. I have to think about. So normally, yeah, you can normally think about the value of the predictor as being what's defining your partition, but and they define the multi-calibration notion with respect to the partitions. So okay, so I guess like the condition on F doesn't actually change at all because F doesn't even exist in their paper, right? Like there is only the partition. But I think they treat I think maybe what I mean is like I think treat the labels as being subintervals of 0-1. And then have a condition maybe where like you need to that all the covariance shouldn't differ too much between all possible conditionings of the label into all the different categories, but I can't remember their exact conditions, so I'm not sure. Yeah. And you would imagine in this case that we are outputting because I guess like we are coming up with a model rather than a.
Yeah, but like I guess in general, calibration for multi-class problems, if you want full calibration, you have sample complexity that is like exponential in the number of labels, because that's how many basically different predictions your model might make. That predicts the probability of each of the labels. And so like, yeah, my basic question, if I want a similar statement to the multi-class problem, do I need something as strong as that requires data resources growing exponentially with the number of labels, or is some weaker notion of calibration? You don't have to answer it right now.
Yeah, no, I don't think I'll be able to, would not be able to say anything with reasonable confidence right now. So I have to look at the paper again and think about it. Any other questions? No, all right, cool. Congrats on making it through the semester.